I would say that the crown jewels of the Java ecosystem are the specifications. And chief among that is the Java language specification. Not that the millions of Java programmers that work on Java ever need to read the Java language specification. They get their knowledge of Java from more friendly sources, but the Java specification, the Java language specification, provides a solid basis for defining unambiguously what a Java program means. And it has a lot of work put into it, as Brian has just described, in making the Java language something that is worth learning, that is predictable, scrutable. You can write simple code in it. The simple code will do oftentimes what it seems to do. You can write code in Java that is scrutable to other readers of Java code. And most importantly, in order to give Java a long career that is commensurate with, say, our careers, and be useful throughout those careers, Java has to be compatible as it changes over time, because it must change, it must evolve. And yet, if it were to evolve into a completely different thing every few years, then those programmers would have to relearn from scratch. The secret to making this work from the very beginning has been, in my opinion, the Java language specification, which has an unusual amount of care and thoughtfulness devoted to it, even from the very beginning, in making Java be well-defined and predictable with very few dark corners, very little undefined behaviors. And so that's, the specification allows the Java ecosystem to be built on top of a foundation that is readable and is compatible. And then the other crown jewel is the JVM language specification, which even fewer people read than the Java language specification. And very few people, hopefully many in this room, but not very many other people on the planet, need to refer to the Java VM specification in order to do their work, because the Java language and many other VM languages compiles to bytecodes, but then it goes down into it loads into the VM in a process which very few people actually have to think about and worry about. And yet, I will claim, because I love the VM, I love to work on it, I love to see it be used even if it's not fully appreciated by its users. In fact, the best, most useful tool is the one that you forget you have, because you're just doing your work, your tool's in your hand, and it's an extension of your hand, right? That's the way a good VM should be, and a good language, and good libraries, and so on up the scale. So the JVM specification is also something that has allowed people to very quietly and unobtrusively write powerful tools that do what the programmer wants to do without the programmer having to think too much about it. This talk that I'm going to give you is mostly recycled. Some of you have already seen it. Apologies in advance, and there's a link to it. I gave a talk at FOSDEM a few months ago and about VM trends. So I'll try to adapt. I won't say everything that's on these slides, since it's already out there in the open and has been presented already, but I do want to apply it to today's themes. So let's see where we're getting here. Here's Safe Harbor. Okay, so principles for what the VM is. What's in the DNA of the VM, besides being readable and compatible, besides being scrutable? Well, the goals for the VM are a uniform model that is no more complicated than necessary. There's an object model which is flexible enough to be useful in many kinds of applications, and yet there's also primitives. It's not so uniform that it's some sort of just a head trip that somebody decided to make everything out of lambdas, including unary numeral representations. It's not that kind of a purely intellectual system, but it's uniform enough that the pieces feel similar, and it's efficient. It's efficient enough. We know that over time we need to improve the efficiencies, and so with Valhalla we're fixing the data layouts to make them even better. But the VM over the past 20 years, and hopefully for the next 20 years, will continue to be an efficient way to store your data, and not only efficient, but corollaries of efficiency, secure, predictable, debuggable. Not only does the data want to be useful, but the code also. And in particular, Java pioneered a lot of the techniques that we take for granted today of customizing your code for hot paths, doing online customization of code. Before Java, I remember there was some laboratory work on profile-guided optimization, which is now, it's come to fruition. It's a mainstream thing in its own right, but the idea of actually gathering online profiles and optimizing to those and recompiling your code, that's something that Java productized first, at least in a big way. The VM of the future will, I claim, be post-threaded. When I see pictures of dinosaurs like Brian showed earlier, I think of threads. I think of the size and slowness of threads, and I think of the smaller, more right-sized executable elements that Ron and company are producing in Project Loom is much more like the little tiny raptors that run around and, really own the territory. The VM should be interoperable with native systems, with non-managed languages, with C, for example. It has been in the past. I think it will be in the future. This is one of the values we want to preserve. We want it to run Java preeminently, but also other modern languages. And by the way, that shouldn't be an either-or choice. Java needs to be a modern language, and thanks to the work that we're doing, it has every prospect of continuing to be so. And on the other hand, even in 20 years from now, I think there will be cases where we will want to run dusty jars. A dusty jar is a jar that's sat in a virtual IT room on a disk somewhere, and it's just been accumulating dust. Every now and then someone dusts it off and runs it, and they have a mission-critical need that it be runnable every so often. And our concern for compatibility is sometimes borders on the cultish or the maniac, but we think it's important to be able to, given that we have millions, literally millions of developers depending on what we decide in this room, we want to be able to tell each one of those, hey, you have a very good chance of relying on this technology tomorrow and the next day and next year and even 10 years from now. If we're not really scrupulous about keeping the forward and backward compatibility of our systems, both at the language and the libraries and the VM level, then we will disappoint enough of those millions of users that it will consume the rest of our time and resources just to help them through their crisis. So we'd rather avoid that in the first place and make a tool that you can forget that you're using because it works so well. Performance, of course. There's so many different new kinds of hardware coming out. If someone could have told me when I was a young guy just starting to work on Java and VMs and stuff, what kind of hardware we would be dealing with today, I would have been shocked and horrified. But we've got to get used to it. We've got to get used to heterogeneous processing and slow memories, and who knows what next. I wonder how many of us in this room will be doing FPGA work in 5 years. Probably several, maybe many of us. In essence, we have a good buzzword that we use in the Oracle group. Our mission is to keep Java vibrant. Now, if you don't ask too much of that metaphor, because what vibrant means is like a little tuning fork that's sort of oscillating really fast. And I don't know why that's good, but in any case, we want Java to keep jumping around a lot and in some sort of coherent manner, I suppose. So it's going to be applicable to today's workloads as well as tomorrow's and yesterday's. We want it to be compatible, trusted, reliable, all those good things. All the good particular technologies like JIT and AOT. And we want Java to give you not only a high-level abstract programming language, but when you need to drop down and feel the bits between your toes in a memorable old school statement, you want to be able to stand there on the the real metal, past the virtual metal, stand on the basis of the vector unit and feel it humming between your toes. We want to run the world on Java, and that means the new and the old hardware and the new and the old software. That's a small goal, right? Very modest. So here's a laundry list, right, of technical initiatives on the VM level that underlie much of what Brian and Mark have already talked about. I won't go into this for purposes of time, but it's there as sort of a, this is my view of the long-term agenda that I would like to work on with you, and I hope you want to work on with me. If somebody else has a better agenda, let's modify it and make it better for those 10 million Java programmers. But this is my best take on where we want to go. It's too much to go into, so I'm going to flash that slide and move to a more abstract one. This is all online, by the way. You know, if you go to my CR page, there's a presentation folder, and that has all of my presentations in it. So here's 6 maybe coarser-grained trends that seem important and not coincidentally match up with major projects in the OpenJDK. I think that Java being a mature language and increasingly useful for broader classes of application, Java will in fact host itself more and more. Now, are there still Java compilers written there, Java C implementations that are written in C? There used to be, right? The JIKES one? Yeah. I remember the Sun Tools group did one too. But for some reason, Java, the object-oriented language, is a really good language for implementing compilers in. So I think all the compilation technology nowadays that's in use for Java, for compiling Java, is written in Java. The VM has reasons that it has to be coded in assembly language and C++ and other languages like that. But there are similar reasons that the VM should host itself in Java. And so there's bootstrapping problems, which I think if you read the literature of computing, bootstrapping is like a fascinating subject that people can't leave alone from even before, in the days of the punch cards, cleverly bootstrapping your system was like the programmer's zen. And bootstrapping is still difficult. But if we can solve the problem of meta-circular implementation of a Java VM coded in Java, and AOT gives us a new tool for that, by the way. I say new, but it's a very old idea. Then we can begin to benefit from our own language as the implementation substrate for our technology. I'll have a few more things to say about that, but the other points are of a similar nature. They're sort of big areas that we want to move the language, move the system towards our long-term goals of continuing to be compatible, but also being more and more understandable and useful. So primitives and classes somehow caulk the seam or heal the rift. We have a more uniform object model with Valhalla, and I think that's a multi-stage, decade-long trend, which we're going to spend a big part of our career participating in. Let me talk about. Well, let me back up again. I'll give you a verbal on the other 4. Brian has already talked adequately about language support, but I want to say a few words about eventually. This is just the preview of how the VM participates in that, and likewise how the VM participates in access to hardware, getting down to beyond the virtual metal to the physical metal. Much has been said this week already about Loom. I have a few words to say, but nothing really new. And then scale getting scalier, and the big evidence of the big evidence in the Java ecosystem of us scaling up is not only Loom, but also the wonderful GC work with Shenandoah and Z, which I will stoutly argue is the work of one team rather than 2 competing teams, even though appearances may sometimes look different. In any case, the VM is going to continue to run at scale even as hardware gets even more gigantic and strange with multiple layers of memory at different latencies and many more cores and strange interconnections. We are going to continue to serve that hardware well. And now I'm thinking of Brian's picture of the predators and the prey. We're going to hunt elephants. That's our scaling challenge. All right. So this is a new slide. This is my thought for the day. What does it mean to be readable? Remember, readability is one of our goals and our values that Mark pointed out, and I think it's very good. It's very obvious how to apply readability to code. Applying readability to a JVM is a little different, but it can still be done, and I want to give you a few thoughts about how that might work. So first of all, something is readable if it can be understood, if it's scrutable, if it has a well-defined meaning. And that's why I started out by talking about specifications. A specification has to be something where there's a definite meaning assigned to all of the possible statements in some language. And that applies to the VM specification also. So the specification has to be clear and correct and complete, and then also the pragmatics of working with the language of the specification, in this case class files and their behavior, that has to be predictable and so that people can use it and not have to guess as to what their code is going to do. So I have to back off from saying that humans read class files, because they don't usually, although some of us do, right, when we need to or even when we like to. But the VM that does the reading of the class files has to adequately understand and adequately respond to the class file. And it actually matters that the class file has some kind of a good style. There are bad class files out there in bad style, which are hard to read in many of the same ways that bad IDE-generated boilerplate walls are hard to read. And of course, it's not that we like conciseness for conciseness' sake, but conciseness is a heuristic for this can be processed reliably. It won't contain surprises. Large class files are hard to process reliably, and they may contain surprises of both semantics and performance. So there's an aspect of conciseness here too. But the important thing is that when the VM processes a class file, that the results be predictable in practice as well as in principle. In order to make it easier, more predictable, more likely that the class files will have a practical scrutability and predictability, the specification should encourage the creation of class files that are not overly complex. Think about this at the source language level. If we don't have Brian's record feature that he was talking about, which lets us have a data holder class in a commensurate amount of text that is required to define the name and the components of the class, but instead requires gigantic boilerplate methods, then we can't read that class and tell for sure that it's just a dumb data holder. Likewise, the VM, when it loads the larger bytecodes, it can't optimize that class as a dumb data holder. It has to assume, until proven otherwise, that there might be some weird, clever hack trick inside somewhere in the bytecodes of that big, fat data holder class with a wall of boilerplate. There might be something in there that will surprise the optimizer. And so, although we try to be as clever as we can in the VM to optimize code and data, if it's complicated, if the original statement as presented to the VM in the form of a class file is hard to read, then the optimizer may, against all odds, optimize your code well, but it may also fail. And so, although you might find it surprising, one thing I look at when I look at the effect of a language on the VM is I ask how much of an expansion factor is there from the language to the class file. If the language is readable to humans, does the compiler turn that into a class file that's not very readable to the VM? To me, that's a bug, although many programmers would not notice that. They don't care. They've got too many photographs on their disk. They don't care about the size of jars. You know, all their jars will fit in the same space as one full-resolution picture of their puppy. And yet, it matters to me, the size of the class files. Where are our Scala friends? They know about this. They know how one little line of code can produce dozens and dozens of class files. To me, that's a bug. But it's a bug that can be fixed only by upgrading the VM spec to allow the natural expression to the VM of the class file that you want. Okay, so where does that lead us? That means we have to evolve the spec, but we don't evolve the spec, again, by adding boilerplate, by agglomerating, by accumulating, by putting yet another writer on all the other 50 writers in the JVM spec. And this means that when we evolve the JVM spec, and it's also true of the language spec, we want to make things better than they were. We want to clean up something every time we add something. We want, if possible, it's an impossible dream, but to the extent that it's possible, we want to keep the overall complexity of the spec constant even as we add new features that are required. And that means either garbage collecting old features or simplifying old features with an account that reflects our better understanding of them today. And so I'm really proud on the spec work that we did for nestmates, because while we added some new stuff to normalize the concept of what private means across classes, we also improved the accounting of how the invoke special bytecode works. And the invoke special is a very bad code spec smell inside the JVM spec, because it was a dumping ground for all sorts of irregular behaviors that we didn't know quite how they worked. So we just put it all on invoke special. If you don't read class files, you don't know what I'm talking about. But invoke special is a headache for everybody that has to care about the class file format. And I'm happy to say that as a side effect, thank you, Dan, by the way, who spearheaded it, as a side effect of our most recent JVM spec changes, that the invoke special accounting got simpler. And that makes the spec more predictable to the VM. It means we can improve the optimization of it without fearing that we've broken some corner of the semantics of the instruction that we forgot about. So this is why specifications are important, and why readability is conditioned by the readability of the spec, readability of the class file. I took my points out of order. I already explained to you why I think concise class files are not a goal in their own right, but are a heuristic sign that something is going well and have a knock-on effect of being easy to optimize. The big thing about the VM that makes it predictable and usable and readable, I'll use the word readable even, is that rather than being one monolithic design that only exists for one purpose, which is to run Java 1.0 class files, right? That was the original design of the VM, and it was a heroic effort. We want the VM to be increasingly more factorable. If you like the heap, but you don't like the Java linkage model, you can do a closure language implementation that uses the heap, but doesn't necessarily use the linkage model in Java. It doesn't know what to do with invoke special, for example. So the VM should have its individual pieces not only understandable in isolation, so that's a readability aspect, but also usable in isolation, usable in new combinations. Let me give you an example of some of those separable aspects. Of course, the load format for classes. This is evolving over time, right? And we're going to do more with Valhalla in order to solve the problem of templating or reified generics. The class file format is going to take a hit. It's even taking small hits with value types. So as we improve the functional repertoire of class files, let's make sure that the format stays scrutable, readable, verifiable, optimizable, and yet ever more expressive towards the prey that we hope to capture. Likewise, separate from the structure and meaning of an individual class file is the linkage behavior through the symbolic references inside the class file to other class files. And that can be made more and more programmable over time. It is partially programmable now with Indy and Condi and may become more so over time. Maybe that's the right way to solve some complexities with templating, which we are struggling with at present. What about the heap? I already mentioned the heap's a great place to store your data. It's going to be even better as we get flatter, denser data options. And of course, it should be scalable, which means we want to continuously work on improving our garbage collector technology. But the important thing is that the storage of objects you should be able to use the object store without it being conditioned on you giving exactly the right usage patterns of some class file attribute over here and some invoke special instruction incantation over here. You should be able to just use the heap with the straightforward byte codes that don't necessarily come from a Java program, but come from your special application. A JIT and optimizer, super important, including profile, et cetera. The JVM can become more factorable, more separable, more understandable by parts to the extent that the interactions between those parts are teased apart and made into protocols rather than hardwired virtual metal. So that's why I talked about going meta yesterday. The old school term for a way to extend the repertoire of a type system is meta-object protocol, and I think that term also lays well over the kind of VM that we're hoping to build here. And then one thing that is underappreciated about the VM is, it's an operating system. It has a lot of utilities and tools and services that are good and beautiful even by themselves. But those should be deployable by themselves. In other words, you should be able to use the logging system without having to care how the debugger works and so forth. In other words, it's a toolkit. All right. I propose to go launch rapidly through these other slides and make a note for the questions afterwards if you want to go back and talk more about them. But I already talked a little bit about Project Metropolis, where Java should be hosted on itself. The Graal JIT is a key enabling technology here. The Graal JIT is has some very old DNA in it. People have been working on self-hosted Java compilers for a very long time, and now we have something that's really mature and worth starting to put into the main technology under our ecosystem. It's great stuff. Johannes Kepler University had some inspired funding and teaching that led to the existence of Graal, and there's a huge amount of work that's gone into it over decades. So I applaud them, and we're using Graal now for AOT. Oops, too fast. The last point there. So Project Metropolis is going to hopefully guide us towards replacing the C2 JIT. C2 is written in C++. It's a great optimizer, but it's kind of hard to work with. And we think it's time to refresh the technology using a self-hosted compiler at the JIT level as well, since we've been doing it so long at the language level. Anyway, that's watch this space. It's exciting, and let's work on it together. I mean, the work in Metropolis is going to take years. It's going to be rewarding and also frustrating, and it needs multiple hands on it. It's not something that just a few people can do. Yeah. What I hope to get to in the end with Graal is that there's a unified code pipeline where when the VM needs to generate some special kind of online code, or even doing offline generation of itself beforehand, it uses a unified technology that we control, which will be Graal. And so this is maybe a little bit controversial, but I don't want to depend on LLVM, although LLVM is a great technology, and you guys at Azul are making good use of it. But for the long haul, even though I love programming in C and C++, I like Java better. And I think it's possible for us to have our own code generation pipeline that is really optimal. Maybe there's a sharing situation where we can sort of exchange modules across the boundary with the LLVM people. But in order to control our own fate, I think we need a code generator pipeline that is good enough for most of our purposes, and maybe, especially all the everyday ones. Maybe the top tier compiler can go, fly off like a falcon and use LLVM. That's okay. But our destiny should not be dependent upon LLVM, which it is today because we use C++ to implement our system. Ultimately, I would like our code generation to go through a native Java pipeline for most purposes. Okay. I want to skip this slide. That's not so good. Go to Valhalla. So I don't want to belabor the point, but there's a few places where the VM has to do some deep cuts in order to do Valhalla. I want to say a few more words about that, double-click on it a little bit. Codes like a class, works like an int. That's great. This is, by the way, when we say that to ourselves, it helps recenter our priorities. If we get all too much in our heads and say, well, why are we doing this? This is really weird. It does actually help to refocus and redirect ourselves to remember that we're just trying to keep our classes but have them work more like ints. But when you, so that's a good top level. We find it super useful to refer to that over and over again. But what is it about an int that's different from today's Java objects? And that's an interesting question. And the answer to that is, gives the reason why it's so hard to adapt the JVM in the directions required by Valhalla. What an int is, it's not that an int has something more than a Java object. Java objects are extremely flexible and powerful. You can even synchronize on them. Each one has its own monitor. It has a hash code. It has a zillion methods on it. We would like actually an int to have a hash code and methods on it, but there are things that the int has not, that the int fails to have, that are equally important. An int can be copied around freely, and each of the copies of the int are the same. That is not true of an object. An object has one pointer and one object identity and one set of mutable state. And that is something that the int lacks, and it's not like we need to add that to ints, so you can change 42 to 43 by pasting a bit through the pointer. No, it actually hinders optimizations it would hinder optimizations of ints if you could do that to them, right? Because you would never know whether you actually had the right count in your hand, because it might change under you because someone will side effect it. But removing and retracting object identity from value instances is an extremely invasive change, perhaps the most invasive change we've ever attempted on the VM. But that's what's required in order to code like a class, work like an int. And it's going to lead to a more uniform and powerful programming model, but it's going to be hard. Another thing that's almost equally deep cut in the VM is full parametric polymorphism, where you can have classes which are parameterized over primitives and values, as well as polymorphic pointers. It turns out that erasure is a great trick, but we have to wean ourselves off of it. Erase generics means that at the VM level, every parameterizable value is just a pointer. It's just a pointer to an object with a header. Nothing to see here. The VM just sort of does dynamic tests on it to do what it needs to do. If you have a list of strings, then there's going to be some dynamic tests to make sure that untyped pointer is a string where it needs to be a string. If you have layout polymorphism instead of just simple pointer-based polymorphism, then these tricks fall apart and you have to do something much more difficult. So we're going to there's some big engineering to be done in the next year or so on template classes where, and by template I mean it's kind of like C++ templates where the polymorphism has a much wider scope of activity, and you can have classes, you have one class expand to many different species, many different shapes. It's going to be difficult, which means it's going to be fun and rewarding when we get it done. All right. I'm going to skip this and this. You already saw value type theory. The parametric polymorphism will unlock not only values with generics, but it'll also allow us to, like Brian pointed out, look at streams and other APIs again and simplify them. So this is a case, in order to make, once we make template classes or reify generics more expressive, then our APIs over time can be designed to be simpler and simpler, and our new APIs don't have to have the same workarounds in them. One of the things that I'm looking forward to doing at the VM level with better generics is this project which has been on hold for a long time, which I call Arrays 2.0, which is basically to take the rift between objects and arrays in Java and heal that rift by making arrays more like objects. I think arrays are really good. I mean, arrays make you angry when they don't do what you need, but imagine not having arrays in Java. Imagine having to like work around with, I don't know, linked lists or something in order to do variable length types. So Java having primitives and Java having arrays as bespoke built-in thingies is an inspired move, and it lets us get a lot done. However, it will give us a more uniform programming model over time with investment in the VM to make both primitives and arrays look more like objects and vice versa. One thing that's going to come very quickly with generics is you saw, perhaps you saw my demo of Panama, and you saw there's a pointer type. Pointer to byte it turns out to be a real C pointer wrapped with some type and bounds information. That will be, with true templates, with reified generics, those types will become much more naturally close to what they are talking about in the C language. So you'll be able to say pointer to a byte or a pointer to some value type that comes from C. So I'm looking forward to that happening, that being unlocked and enabled as soon as we get real generics. Okay, it's hard. I won't go into that. It has great impact. I won't go into that. I hope we'll have some breakout sessions to talk about template classes this week, maybe even today. Brian's already mentioned some of the VM work that we've got in flight. Nestmates are done. Yay! That's great. Sealing is on the books. We've got some. That will allow before we had nestmates, we had to break encapsulation boundaries and create sideways access paths between cooperating classes from the same compilation unit. And one of the code smells from that was it caused methods to appear in class files that didn't have any other use other than to open up a hole through an access control layer. Those are the adapter methods, right? Or bridge methods, what do we call them? Accessors, something like that. That was a code smell, and in part, by removing the need for that, the class files get smaller and they say what they mean more clearly. And we'll be able to do that with other similar targeted features which are small, even though no VM feature is ever small. We are also working on the more direct access into the structure of the class file, like with Brian's work on constants. And then the constant pool enhancement will continue, and we had a great talk about that earlier, so I won't talk about that now. But I'll just point out that I think we want bootstrap methods everywhere. At least that would be my preference. Maybe there's a natural limit to that, but I haven't found it yet. But all of these kinds of low-level features are not just motivated by, well, Brian came up with a really neat feature, so I'm going to give you the bespoke VM virtual metal, which will support exactly that feature and no more. No, the VM is a toolkit, and so both at the language level and the VM level, the real deep game is find the primitive. Factor your features apart until you find the low-level primitives that's underlying, that's the implicit assumption underlying all of them, then recompose it from there. Recompose it in an artful, beautiful, useful way, but don't neglect defining the principles and the underlying primitives first. So that means there's some new kinds of finality that we want to invent, for example, that have their own justifiability just at the VM level and then are useful as tools to build up language features. So I'll just point out frozen arrays, and we're starting to talk about lazy statics also as low-level features which you can build better systems on top of. You saw a demo of Panama. Panama is about getting direct access to hardware. I think this is an important overall trend for the VM, that we will be able to not only have Java call itself within a managed runtime, but also call out to that LLVM coded code out there. It's not going away, and we need to handshake with it as efficiently as possible. So, we're making good progress on that. And not only on calls to native entry points, but also to access to native data, in particular vectors. Whatever the hardware throws at us, if a new kind of Rhino with vectorized nose horns comes at us, we want to be able to predate that kind of animal too, regardless of the fact that it has 128 or 256-bit nose horns. That's not a very good metaphor, but we'll move on. So one way to think of Panama is we code in Java, but the code works like native. Sounds like a good slogan, huh? We saw demos of the Vector API. Thank you, Intel, for funding that work. That is beautiful stuff. That, in my view, if we were to have several other major partners like Intel fund similar deep fundamental projects, the Java ecosystem would double in power if we had that kind of funding for the other items on the lists that we've got here. So you non-Oracle people out there that have the ear of your bean counters, please look at what Intel did and help us like they did. I'm going to skip this one. Loom is awesome. Thank you, Ron. Great progress. Thank you, Alan. We look forward to a great future with post-thread concurrency. I'm going to skip these slides. You can read them online. No need to go over them. Sorry about the builds. Okay. Finally, the last trend that I previewed for you is scale. Scale means using your resources better, and also being able to use larger resources. Gil, I liked your talk about predictability, and I like those charts about where it's going slow and how we move fast, a better use of resources into those upper left corners where the VM takes too long to warm up or pauses down too much. I think those are the right kinds of thoughts. I like what you said about predictability. I think that's part of the solution. And in general, I just stand in awe watching what the GC groups have done, and what we've done with AOT to more effectively use our large resources, get them online faster, and keep them online more reliably. So thank you for that. The most I can do with that is cheerlead and care about it. And maybe that's the empathy part that Brian talked about. I really don't know very much about the GC technology, but I will do everything I can to make sure that it succeeds. So let's keep working on this stuff. I think we have an opportunity to work as a community in a healthy way, where we actually pick great algorithms and use them and make sure that they're available to all. And the short-term tasks that I refer to on this slide was from last February about refactoring the GC interfaces and so forth in order to unlock several of these technologies so we can rapidly evolve them. And that's, a lot of that is committed now and done. I really like the willingness of the GC people to refactor their frameworks so that they can all work together on one platform. So yeah, it's the toolkit idea again. I'm going to skip this. I'm going to skip this, and I want to say this is from my talk at last year, which I hope some of you thought about a little bit, which is one of Java has technical debt in it. And some of the technical debt is designs that were right in the late 90s that aren't so good now, like objects with their own lock headers, with their own identity and mutability. You could do a lot with that, and it turns out you can do too much with it, and so the optimizer chokes. Likewise, the Java memory model is very powerful, very flexible. It's predictable enough. It's unpredictable in ways that allow the optimizers to get in and do some useful things with it. But there are some problems with the Java memory model in that if you code arrays, then the Java memory model very modestly says, you know what? You know how the LLVM will give you random code if you have integer overflow? Well, I'm going to do that if you have a race condition. And JVMs are usually don't act out really badly when you make a race condition. They do something that's kind of reasonable, but they're not required to. And so there's some technical debt here. We don't act out as much as the current compiler front ends on the C side do. They've been like getting more and more angry about indeterminate behavior, if you've noticed. If you code with C, each new release will give you more warnings about undeterminate behavior and then actually compile indeterminacy into your system because you forgot about an integer overflow. I'm glad we're not doing that. I'm glad we value predictability in the Java world. But the Java memory model is a place where bugs hide, and race conditions in particular can unlock bugs in surprising ways. And as hardware gets more and more concurrent and interesting, memory gets more and more networky, then race conditions will cause more and more unpredictable behavior for real, even though we don't intend to do so and won't act out intentionally. We'll do it unintentionally. So what does that lead to? That leads, I think we need to be thinking, and this is where we need to help each other and even fund each other's work on this. We need to think about how to make objects more reliably confined to threads, or in other ways, less racy. We don't want to say to the programmers, here's a nice, safe language, except for the race conditions. We've installed child-proof locks on all of our cabinets, but Junior, don't walk over by the snake pit in the corner of the living room there. That's where the race conditions live. So if you have safety and security on most of your house, but there's a race condition snake pit in one corner, your house still has a problem, and you need some more childproofing. All right, so confinement of objects is, in my mind, major technical debt. Why aren't we working on it? Well, we've got other major technical debt to work on too. You know, we have to pick our beasts, pick our prey, and we're going after the flat data right now in the biggest way. And yet, we can walk and chew gum at the same time. We can think about multiple things at the same time. So let's work on that long term. This is my commercial for fighting race conditions. Okay. There's a lot more to say, but I'm going to stop here, okay? Let's do these things together. That's my high order bit. I want to cheerlead your work. You want to cheerlead mine. Let's work on it together. We can't afford to have bystanders. We need active participants. We need to be stewards of this stuff. Thank you.